Okay, well, those were the homework questions that I gave, so let's go through them. Here we have a phase diagram for the lead-zinc system, which has number 1318, has a two-phase liquid region, liquid 1 plus liquid 2, with a critical point which is up around 1075 degrees and displaced over towards the zinc side. So I ask you then to find then the excess Gibbs energy is given by, well, you know, we haven't talked about this formally, but it is a subregular solution. The excess Gibbs energy is, if you had one term it would be regular, but clearly since the miscibility gap doesn't have a peak at 50%, it must be at least subregular. So let's put into two parameters, and the total Gibbs GXS of course is going to be positive, as you know, to give a miscibility gap. Critical temperature was measured at 1065 and the composition was measured at 0.71. So the coordinates of the maximum point are about 1065 and 0.71. And I said, okay, you find the, calculate the constants A and B using the fact that the second and third derivatives are zero at the critical point. I hope you realize why that's the case. Let's say we're plotting here. This is the Gibbs energy of mixing going from lead to zinc. The Gibbs energy of mixing, if you're below the critical point, the Gibbs energy of mixing is going to look something like this. So this is T is less than T critical when you're in the two-phase region. If T is greater than T critical, then it's going to be convex everywhere. And T exactly at T critical, it's where you just flip from one to the other. So now if we were to plot the second derivative, let's say d squared delta G dx zinc squared, second derivative is the rate of change of the slope, so of this curve. So the slope is, if you go from left to right, the slope is positive and becoming, here's this curve, slope is positive, becoming more positive, so the second derivative is positive. Then the second derivative goes through zero at the inflection points. Now the second derivative is negative because the slope's becoming less positive. So your second derivative, if you were to plot a zero here, the second derivative is going to look something like that. These 2 points here corresponding to the two. Okay, so the second derivative. This is for T. This is for T is less than T critical. The second derivative is going to look like that, going through zero, going from positive to negative. If T is greater than T critical, then the second derivative is going to be positive everywhere. And obviously when T equals T critical is just the point at which the second derivative just goes to zero at one point, or in other words, when these two inflection points become the same point. Okay, so you would have here, this is T equals T critical. Okay, so clearly then the critical temperature is the point at which temperature just goes to zero at one point, and that point will be the critical point. Secondly, now it's clear that that goes to zero at the minimum value of this second derivative curve, which, so the slope of the second derivative is also zero. In other words, the third derivative is zero. So the two criteria are, for the critical point is the second derivative is zero and the third derivative is zero at the critical point. That then permits you to calculate the two constants A and B, because now you have two equations. Okay, so if we went to the answers, then what I've run is the excess Gibbs energy then is given by the equation you were given. It's the second derivative of delta G, not the second derivative of GXS, but it's delta G. So the delta G of mixing is the ideal mixing term plus the excess term. Okay, so we calculate the first, second, and third derivatives, remembering that dx1 equals minus dx2. And we set the second derivative to zero, the third derivative is to be zero. We get two linear equations in A and B, which we can solve for the, putting in the critical temperature and the critical composition, we end up solving for A and B. Have any questions about this? So, of course, that just uses the critical point. That doesn't necessarily. So we've used the measured critical temperature and composition in order to calculate A and B. This is rather Probably something you wouldn't do in practice, the reason being that the critical temperature and pressure it's really difficult to measure the critical. Maybe even the critical temperature is hard to measure experimentally. The critical composition, this thing is really flat. So knowing where the critical composition is pretty difficult. Nevertheless, you can see how it happens. The better way, of course, would be to take several points at lower temperature where you know the compositions of the two phases in equilibrium, and you do optimization. Okay, but I'm just trying to show the thermodynamics of the thing here. Okay, so the B parameter gives you the asymmetry. Clearly, if the B parameter is 0, it's going to be 0 at 50%. So in this case, the A parameter, this was the X2 was zinc. So the A parameter should be positive. The B parameter should also be positive. No, the B parameter is negative. How do we get that? Oh, BX1, okay. So in other words, this GXS is positive everywhere, but it's even more positive as you go towards the zinc. Okay, so if this is B times X lead, the B will be a negative term. Any questions about that? So the B is the asymmetry term, and the A is A minus BX1. A plus BX1 is the overall BXS term. All right, let's go to number 3 then. Slow down. Go too fast. Numbers. Okay, here's your bismuth-cadmium phase diagram, which we're taking to be a simple eutectic diagram. I have simplified this a little bit. There's actually a little bit of solid solubility, but let's say there isn't. From the bismuth-cadmium diagram, slightly simplified, calculate the activity of cadmium in the liquid phase at X cadmium is 0.7 at 212 degrees. Okay, so X cadmium is 0.7 would be over here. Did I say cadmium? X cadmium is 0.7 when T is 212 degrees. So 0.7 is here, and 212 degrees is somewhat above the liquidus. No, sorry, this point is on the liquidus temperature. So 0.7, we'll present 212 degrees is on the liquidus. Okay, so calculate the activity of cadmium on the liquidus. Secondly, calculate the activity of cadmium at the same composition, but at a higher temperature of 627 degrees Celsius. So we're going to calculate first of all on the liquidus at 70%, and then at the same temperature we're going to calculate, at the same composition we're going to calculate it at a higher temperature. And what you're given is, you're given the heat of fusion of cadmium at the melting point of cadmium over here, and the partial heat of mixing of cadmium at that composition. And it says state your approximations. Okay, so the first part is simply calculating on the liquidus line. So we use the equation that we use for the liquidus, remembering that there is no the equation along the liquidus and solidus in equilibrium. We have the equation here, RT log activity of cadmium on the liquidus. Things are so bad. On the liquidus minus the activity on the solidus equals the heat of fusion. This is the assumption, of course, is that the Cp liquid equals Cp solid. We're using a simplified equation to make it easier to do it with the calculator. Okay, 485 Kelvin, that's 212 Celsius. The activity of cadmium in the solidus is 1 because it's pure solid cadmium. Okay, so this term goes to 0. So RT log activity of cadmium on the liquidus is minus the heat of fusion, 1 minus T over T fusion in Kelvin. And we get activity of cadmium is 0.76 at the liquidus temperature at 0.7. Okay, yeah.
If the CPU K-1 is different,
then the heat of fusion, well, yeah, then well, the right-hand side of this equation is actually equal to minus delta G of fusion. Okay, which is equal to minus delta H of fusion minus T delta S of fusion. I'm assuming, if we assume that the heat of fusion is constant with temperature, then we get the delta S of fusion, and this is equal to delta S of fusion. Delta S of fusion is T fusion times delta H of fusion at the melting point, because at the melting point delta G of fusion is 0, so the delta S, and so if delta S and delta H are independent of temperature, this is only true strictly at the melting point, but if delta H and delta S are independent of temperature, then you can substitute that back in here and you end up with that equation. If they're not independent of temperature, then and they'll be independent of temperature if Cp solid equals Cp liquid. If they're not, then the heat of fusion at any temperature T was equal to the heat of fusion at the melting point plus the integral from T fusion to T of Cp liquid minus Cp solid T. So this becomes a function of temperature, and that becomes a function of temperature. Or maybe there's a minus sign you have to think about. Okay, so the heat of fusion is the heat of fusion at the melting point plus the integral of delta Cp dt. You agree with that? Okay, and the entropy of fusion is the heat of fusion is the entropy of fusion plus the integral of delta Cp over T dt, and you get an expression for it. If you're doing it using a computer, I mean, this is automatically done for you. It's not necessary to do this. This equation does not depend upon, I mean, if you have Cp liquid and Cp solid, then you can do it correctly. And we do have Cp liquid and Cp solid for cadmium. I just don't want you to spend all your time doing this question with your hand calculator in 8 terms and your integral of Cp dt. This is not, you would never do this in practice. If you have this delta Cp, you would use the delta Cp. Okay, so this gives you the activity of cadmium on the liquid is based, you're assuming that the solid solution has negligible solubility, so that's equal to 1 on the solid, so that term becomes 0. But the point in here is this gives you, now you can solve this at other temperatures along the liquidus, and this gives you the activity of cadmium non-isothermally along the liquidus. Okay. And the activity of cadmium at any composition, the activity of cadmium varies with temperature. Okay, so this would give you, this gives you the delta, so the RT log activity of cadmium, so the activity of cadmium on the liquidus then, okay, that's part B, sorry, okay. So the activity of cadmium, so this gives me the activity of cadmium is 0.76 at 485 degrees. Okay, so what I'll have is the partial gives energy of cadmium is RT log activity of cadmium, and I can calculate that value, so that's equal to the heat of partial heat of mixing minus T delta S of mixing. The RT log activity is the partial heat minus T times the partial entropy. Okay. Okay, so the partial heat has been measured in a separate experiment. The partial heat of mixing of cadmium is 982. This can be measured in different ways, but generally it's measured as a heat of mixing. You go from whatever, bismuth to cadmium. The heat of mixing is measured in a mixing calorimeter. You get experimental points to measure the heat of mixing in a mixing calorimeter. They mix cadmium and bismuth, mix them together, measure the heat that's given off. Okay, heat of mixing, in this case it's positive. And the partial heat of mixing of cadmium, then you measure this curve as a function of composition, take the slope over here, and that point there is the partial heat of mixing of cadmium. So the partial heat of mixing of cadmium has been measured in an independent calorimetric experiment, not the phase diagram. The phase diagram doesn't give you that. Okay, so that's generally the way you would get the heat of partial heat of mixing of cadmium. You don't measure directly, you measure the integral heat of mixing at different compositions. Take the slope, where you fit this up to a polynomial. You don't have to do it graphically, you fit it up to an equation and get the slope. That gives you the partial heat of mixing of cadmium, and you do that at your composition of 0.7. And I've taken that from another experiment, that the partial heat of mixing of cadmium, when the mole fraction is 0.7, is equal to 982. Okay. So I now have the delta G at one temperature. So this gives me the delta G at one temperature. If I want to extrapolate to other temperatures, I need delta H and delta S partial of cadmium. one or the other. I can get one, I need one. So I have the partial heat of mixing of cadmium. I can now, at 485, I have the activity, I know the activity of cadmium at 485, so now I can work out what the partial entropy was as well. Okay, so this now I have this equation here, the delta G RT log activity as a function of T. I have the delta G at one temperature, and I have delta H. So I can calculate delta S, and I get delta G as a function of T. So now I can calculate delta G at any temperature, and I can get the activity at 900 Kelvin. I've made another assumption, of course. I've assumed that the heat of mixing is independent of temperature. Okay, otherwise, this is the heat. This would only be the partial heat of mixing. The heat of mixing and the partial heat of mixing also are not independent of temperature. They depend upon delta Cp of mixing. But in most of these high temperature things, as long as we're dealing with a reasonably small temperature range, it's a reasonable assumption to assume that the heat of mixing is independent of temperature, although this is an assumption that is probably made too often. We make that assumption, sometimes we make that assumption and it really isn't justified. On the other hand, it's rarely the delta Cp of mixing is rarely a very large value, so it's a halfway decent assumption. Okay, but the point here is that just measuring the liquidus gives you the activity along the liquidus. It gives you the partial Gibbs energy, or delta mu, which is the same thing along the liquidus, but it does not give you the value of the activity at any other temperature. For that, you need additional information. There are many assumptions here. We assume the delta Cp was 0 for fusion. That isn't really that necessary. We assume the heat of mixing was independent of temperature. That's a less valid approximation, but probably reasonably accurate. We've assumed the activity of cadmium in solid is 1 because it's essentially pure solid. All right. Then we see the activity has varied by a reasonable amount. The activity at 485 was 0.76. At 900, it's gone down to 0.68, so it's not a trivial change. Now you can also see, as I said last week, suppose that you decided to, okay, you can say, well, here I've got delta G cadmium at one composition on the liquidus, then I need the heat of mixing. Well, hubby, I can do delta G, I can do the same thing at different compositions along the liquidus. I can do it at different compositions along the liquidus. At 0.7, 0.8, 0.9, 0.6. Okay, and then I get delta G of cadmium is delta H minus T del S of cadmium at a number of composition temperature coordinates along the liquidus, and I could probably then now I have 2 or 3 points, so I could take this equation and solve it at smooth it out in order to get delta H and delta S from my non-isothermal calculations along the liquidus, but this would be completely wrong. There's no way you can separate delta H and delta S by a non-isothermal measurement. Okay? You're making an assumption. You're making an assumption that these are independent of, well, I don't know if you're making an assumption, but it doesn't work. Okay? All right, so that's to show you how that works. And again, what you're doing is often, I'm doing this by hand because when you do it with the computer, you miss what's really happening. If you did this if you were doing this optimization in the computer, you would have the phase diagram, you would have the heat of mixing, and you'd optimize the two things simultaneously to get your whatever power series you want. But this is what's really happening. Okay, you can't get around that. What you're doing is at the liquidus points, at every point on the liquidus, you're using this equation, or the computer is using this equation to get the activity on the liquidus, and then it's using the partial heat of mixing in order to integrate up in temperature to get you the activity or partial Gibbs energy or whatever at the higher temperature. This is what's really happening. If you're looking at the air limits, if you're trying to judge the air limits, even though it didn't do it exactly this way, it's what the computer is doing is exactly equivalent to this. Okay, and the air and going from here to here. Okay, if you want the activity, what is the air in calculating the activity at 900 relative to the activity at 485, it's based entirely upon the accuracy of this delta H cadmium term. That is the term that's going to determine the difference between these two things. So Okay, this is to show you what's really happening. If you did it by hand, you'd have to do it this way, and there's no getting around. That's what's going on. Questions? Okay, number 4. Okay, the silver potassium chloride system is a simple eutectic system with negligible solid solubility, so just a simple eutectic thing. Suppose that this liquid is ideal, calculate the temperature and composition of the eutectic point. Given the 2 heats of fusion and the 2 temperatures of fusion, well, this is really pretty straightforward. So that's what the phase diagram looks like. It's a simple eutectic, no solid solubility. And you have the eutectic composition and temperature, and I'm assuming a liquid that's ideal. So you have the equation basically of this liquidus line. And the equation of this liquidus line is RT log the mole fraction, well, take out the E's here. The equation of this line is RT log activity of silver chloride on the liquidus minus RT log activity of silver chloride on the solidus, which comes up to be 0, is equal to this. Okay, so I'm saying this equation here, RT log activity, equals the heat of fusion, again assuming the delta Cp, the fusion is 0, applies at all temperatures. It also then applies at the eutectic point. So this equation would apply everywhere, but it also applies at the eutectic point. So if this is the temperature of the eutectic, this will be the mole fraction at the eutectic. Here I've made the assumption, of course, that the activity is equal to the mole fraction. So I assume the activity is equal to the mole fraction. In other words, an ideal liquid, I'm assuming the activity in the solid's 1, so the RT log activity in the solid term goes to 0. And this applies everywhere, so when the mole fraction of silver is equal to X eutectic, the temperature is T eutectic. So there's one equation from this point, and then on the other side you have the equation of the other liquidus, which is just replacing mole activity and mole fraction of silver by the activity and mole fraction of KCl, which is 1 minus X silver. So you have 2 equations, 2 unknowns, X and T, and you can solve. And it comes out actually fairly close to the solve the 2 by approximation, by successive guessings. You end up with 2 equations here, logarithmic equations. It's T, but I mean you can just take successive approximations and narrow in on the right answer within a couple of minutes. I think this is within about 15 degrees and a couple of % of the actual point, so this is actually a fairly ideal system. All right, just to show you what if you go to number 15, this is the one we talked about at length last week, was that you can actually use the equation going the other way around to actually you can use a liquidus measurement in the dilute region in order to measure a heat of fusion, which is often very difficult to measure at very high temperatures. So the melting point of niobium is very high, 2467 degrees Celsius. Platinum is insoluble in solid niobium. The liquidus temperature when you have 1 gram of platinum and 99 grams of niobium is 2456. Calculate the heat of fusion, the enthalpy of fusion of niobium. Alright, so we go to number 15. Alright, so as before, here you have niobium, over here you have going to platinum. You have the liquidus temperature here. This is T naught of fusion of niobium, and this is at X platinum, which is quite small, and this is T. Okay, so you measure the change in temperature as you add a small amount of platinum. How much platinum? I measured the mole fraction. Actually, this point here is X. I converted from weight. I had 1 gram of platinum, so I converted to mole fraction. The mole fraction of niobium at that point is 99521. So you've measured the melting point of the pure niobium and the melting point in a thermal analysis experiment probably, and the melting point at 1 gram of platinum, 1 weight %. Found a temperature difference of 11 degrees. Okay, so then we have RT log activity. Now you're assuming, what are the assumptions? This is RT log activity on the liquidus equals the heat of fusion and so on. The assumptions are that the solution is ideal. I've replaced the activity of niobium by its mole fraction. But this is always true if you're in a very rich solution, very, very dilute in platinum, because Reynolds law always applies as you go to the limit. So as you go to the limit of pure material, the activity of the solvent always approaches the mole fraction of the solvent, Reynolds law. Okay, so, and less than 1%, a half a mole percent is probably pretty close to the limit here. So we're making the assumption of an ideal solution, but it's a good assumption because you're in the limiting region. I'm assuming, again, the heat of fusion is independent of temperature, but I mean, we're only talking about a very small temperature difference here, so really as you get very, very close to this, this approximation really isn't a problem because you're taking the limiting slope. Or in other words, the heat of fusion is going to be pretty much constant over 11 degrees. And we've got to assume that there's no solubility of platinum in the solid niobium. Otherwise, you would have a minus RT log activity solid term here, which would be unknown. Okay, and so we end up then from this getting the heat of fusion. And of course, this would be the same as you pointed out last week. It doesn't matter platinum, no matter what, you can put any material here, any other metal, as long as it was insoluble in the solid niobium, you would get the same liquidus point in the limit as X niobium approaches 1. If you, of course, gets more concentrated, then the various liquidus lines are going to be different. So what you really should do is, of course, even at 1 weight percent, it might deviate a bit. So what you really want to do is you want to measure a few points and then with your ruler make a limiting slope, taking the slope as the mole fraction approaches 1, and then all the approximations drop out. Okay. And this is a more accurate way of measuring the heat of fusion of something with such a high melting point than calorimetrically. Calorimetrically, you're never going to measure something like that at that temperature, but this is a reasonable way of measuring the cooling curve is an awful lot easier than measuring calorimetrically. And also, this is a check. If you find that the measured limiting slope does not agree with that equation, well, no, let's go the other way around. Let's say you have a material now in which you do know the heat of fusion, lower temperature, you do know the heat of fusion from calorimetric measurements. Then you can use this equation to check for solid solubility. If this limiting slope agrees, if the limiting slope agrees with that equation from the measured heat of fusion, then you know that you have no solid solubility. If the limiting slope is a bit higher, then that would indicate you have some solid solubility. If the limiting slope is lower, it indicates that some of the thermodynamic data got to be wrong. Okay. So checking your limiting slope is always a good thing to do. Okay, many questions? Number 12. But see, the limiting region is measuring a phase diagram. Even if you're talking about the entire, you're measuring an entire system, we're not just in the limiting region. Measurements in the dilute region are important because in the dilute region, this entire equation becomes independent of G excess. And it's only the ideal terms that matter. So right away you can get some pretty good indication about your solid solubility, whether things are correct. Okay. Again, you see it's kind of masked. Suppose that you had some measurements. Say you're trying to optimize this thing and the measured liquidus is here. These are some measured liquidus points. And you're fooling around with your optimization and you're trying to bring in your G excess terms and your power series, and you find that no matter what you do, you're really having trouble getting these points down here. You see, you got your liquidus points are like that. You often find this, I've seen this in papers. These are the measured liquidus points. And you're trying to fit this, and well, you got to fit, but you just can't fit these points here. Why can't I fit those points here? You add a whole bunch of extra G excess terms, you put cubic and quadratic terms, and you still can't fix the thing. The reason is that in this limit here, the G-excess terms, as you approach niobium, the G-excess terms become less and less important, have less and less effect. As you reach the limit, they have no effect. This limiting region is determined by the ideal term. Okay, and if this goes down like this, then if your measured points were up here, and you trusted the measurements, then that probably indicates you have solid solubility. If they're down here, probably there's just something wrong with those measurements, or maybe something wrong with your heat diffusion, or something's not right. But you can't fix this up in the limiting region. In the limiting region, you can't fix up your liquidus just by adding more G-excess terms, unless they're huge, and that's just not right. You can add very big G-excess terms, which will kind of bend this in, but it's going to throw everything else off over here, because that's not the problem. The problem is the ideal term, the experimental data, the heat diffusion, something is wrong. So again, I'm going to show you the factors that affect phase diagrams. You shouldn't just use the optimization and put things in. You got to think about what's really, what terms are influencing the diagram. Just as I said in the previous example, that the number 3, where what determines the change of activity with temperature, that's the partial heat of mixing term, and so on. Okay, number 12.
Excuse me, you mean like by excess term 0 to 0 that terms in the like classical?
I mean the G-excess, yeah, the terms that you're optimizing, the parameters that you're optimizing. I mean, what term?
Like, you mean that we don't really need G-excess when we are reaching the
I mean, in the limiting region,
the
G-excess will have no effect on this term, on this limiting slope.
Yeah, I mean, when, for example, we use like 2, 0 for one, like niobium would be 2.
You're talking about the quasi-chemical?
Yeah.
You're talking about the Z? The coordination number?
Yes.
No, that's nothing to do with it. But yeah, that will have no effect either. Yeah, that would have no effect. I'm talking about the terms, that the expansion terms. You have x1, x2 times a plus bx plus cx squared plus d, these terms. What you call them, the q terms, the qij
Yeah, but they have
terms,
power,
and the z.
yes.
Yeah, but none of these terms have any effect. No G-excess terms will have any effect on the limiting slope. It's only affected by the ideal term, and the heat of mixing, and the solid solubility.
Yeah.
But G-excess in the liquid will, if you take the calculated liquid as here, as the closer and closer you get to the pure niobium, the less and less effect any G-excess term has on it, only the ideal mixing term. Now we'll talk later, there is one thing where it does make a difference, but I don't want to get too far ahead of myself. And that is, it depends only on the ideal mixing term, the ideal mixing term being the configurational entropy term. And that does have an effect if you have, well, I'm getting too far ahead of myself, I just want to show you here. We'll talk about this later, but let's say this was sodium chloride. And I'm measuring the limiting liquid slope here. And if I add in potassium chloride here, then I'm going to get the limiting slope, and if I would put in, I don't know, rubidium chloride or silver chloride, I would in the case always get the same limiting slope, just as I did adding that with niobium, because I'm adding one more. Okay, but let's say I added potassium fluoride instead of potassium chloride. Now the potassium and the fluorine ions basically go in as 2 independent particles. The ideal mixing term is not what it was before with potassium chloride, now it's 2 times. The potassium ion and the fluorine ion each mix independently, so they give you twice as much entropy. So I'm going to get exactly twice the limiting slope. So the limiting slope also tells you how many independent particles are being formed. Okay? Because in the limit, the potassium goes into sodium chloride and has an infinite number of sites to go on, and the fluorine as well. So you have twice the entropy, and that gives you exactly twice the limiting slope. Okay? So the limiting slope then will also tell you how many new particles are being added as you add the... In fact, this was the first evidence back in the 1940s that molten salts were in fact ionic liquids. And when they added potassium chloride, they got this slope. When they added potassium fluoride, they got exactly twice the slope, indicating for sure that the potassium and fluorine were dissociating. They weren't going in as a molecule, they were going in as 2 independent ions. if I were to add potassium sulfate, okay, I would get a slope with 3 times the slope because I got 2 potassiums and 1 sulfate. But the sulfate, of course, doesn't dissociate into sulfur and oxygen, it stays together. So once again, just putting K2SO4 in dilute solution in sodium chloride, I'll see the limiting slope will be exactly 3 times what I will get for 1 particle. And again, this is independent of all the excess terms. It depends only on the ideal mixing term, how many particles it dissociates into. So it's a very fruitful area to measure, to do experimental measurements. They're fairly easy to do, and you get a lot of information because it becomes independent of GX. Okay, and ternary lithium sodium potassium fluoride. This is an old question. Is one uses the molten salt and the for the heat exchanger and nuclear reactions and reactors in the USA. Well, they don't anymore, but they used to. You would like to know the composition and the temperature of the ternary eutectic. Well, this is just the same. I calculate the. This is exactly the same as question 4, except it's for the ternary. What number was that? It's exactly like the question 4 would calculate the eutectic temperature in the silver potassium chloride, except now I have 3 equations to solve simultaneously. This is the lithium fluoride liquid to surface, sodium fluoride liquid to surface, potassium fluoride liquid to surface, again assuming no solid solubility, assuming the activities are equal to the mole fraction, in other words an ideal liquid solution, assuming the heats of fusion are independent of temperature. You have 3 equations and yeah, 4 equations actually, because the sum of the mole fractions must equal to 1, so you can solve. Just to show that the equations apply not just for binary system, of course, they apply for any system. And let's look at number 32 then. Probably gone beyond this, right? I'll do so fast I don't have to go backwards. 32. Okay, here you have your sodium chloride, sodium hexachlorozirconate solution. They've been proposed as electrolytes for electrolyzing zirconium. They do work, but you end up getting a dendritic deposit rather than a nice flat one. But, the solutions partially decompose, so if you take your sodium chloride, sodium hexachlorozirconate solution, and above it you'll have a gas phase, and the gas phase will have a ZrCl4 gas in it at equilibrium. So you would have down here you would have your NaCl, Na2, ZrCl6 liquid solution, and up here you'd have a ZrCl4 gas phase in equilibrium with it. Okay, the partial pressure has been measured at that point, at the eutectic point. The partial pressure of ZrCl4 has been measured as 0.06859 atmospheres. Calculate the Gibbs energy of this reaction at 548 degrees. All right, so at that point, in other words. Okay, so this is the reaction that we're interested in, the equilibrium between the 2 salts that are in the 2 components of this liquid phase and the gas phase. And the constant of equilibrium then is equal to the activity squared of sodium chloride times the partial pressure divided by the activity. The partial pressure has been measured, so in order to get the equilibrium constant, from the equilibrium constant, of course, you get delta G naughts minus RT log K. So the delta, to get the Gibbs energy, the delta G standard of that reaction, you need the equilibrium constant from this equation. And now to get the equilibrium constant, I need to know the activities of sodium chloride and Na2ZrCl6 at some point where both, at some composition where both activities are known. Okay. So I can get that, of course, from the eutectic composition, as we did at the eutectic composition. You have, this is the liquidus of sodium chloride. Same thing, RT log activity of sodium chloride is the heat of fusion, 1 minus T over T fusion, that's the activity of sodium chloride. Assuming no solid solubility and assuming a heat of fusion independent of temperature. And then for the other liquidus, you do the same thing to get the activity of hexachlorozirconate. That gives us equilibrium constant because we have the activities, the two activities are two activities of a solution which is in equilibrium with the gas phase. So these are got to be at the activities at the same point. You could measure them at other points, but at other compositions, and you should get the same equilibrium constant, but this is easy to measure because the eutectic composition is the temperature where the two liquidus lines converge, and so you get the activities of both. So that's the only point of the diagram in which the phase diagram gives you the activities of both components simultaneously. Questions? Okay, so then I had number 1817. This was to play around with the this was to play around with the phase rule. Okay, so here we have three what do you see all right, I rephrased this question for you last week, but basically what you have here is you have three phases. We're going to have a mat, we're going to have a slag, and we're going to have a gas, and they're all in equilibrium. And we're saying that you have a the slag phase would consist of copper oxide, FeO, SiO2. It also has got some Fe2O3 in it, of course. It's got sulfur in it. It's got all the things dissolved in it, but it's principally copper, iron, silica. But it has going to have trivalent iron. It's going to have sulfur. It's going to have all these things can be in it. And the mat is mainly a copper, iron, sulfur solution, but it's also going to have oxygen in it. There's going to be a little silicon. Everything's going to be dissolved, but it's mainly copper, iron, sulfur, and this is mainly this. And the gas phase contains everything: S2, O2, SO2, SO3, nitrogen, and a whole bunch of other stuff. And the whole thing's in equilibrium. Okay, so the temperature now is constant at, well, the temperature's constant and the total pressure is 1 atmosphere. Now I phrased this two ways. First way I said all the, well, this is what I said, all the thermodynamic properties are in principle known, and an engineer says then, well, at least in principle, if he can, if he measures the partial pressure of SO2 and he measures the partial pressure of oxygen and he measures the sulfur content of the slag, then he can calculate the composition of every phase, basically. Or in other words, that's enough to fix 0 degrees of freedom. If you fix, basically that's what he's saying, if you temperature, total pressure, SO2 are known, oxygen content is known, and the sulfur content of the slag is known, then the number of degrees of freedom have gone to 0. In other words, at that point the composition of every phase is fixed, calculable if you had all the properties. Or let's put it another way, let's say you have two systems, you have two systems, one furnace here and another furnace here, in which you have gas, slag, and mat in equilibrium, and in both furnaces have the same temperature, same total pressure, same PSO2, same PO2, and the same sulfur content of the slag. Are the two systems identical in terms of composition? Or could they be different? Remember, identical in composition doesn't mean identical in the amount. You could have different amounts of the phases. I'm talking about the composition. Total amount of a phase is not a variable in the sense of the phase rule. Okay, so let's look at the composition. The components of the system then would be copper, iron, silicon, oxygen, sulfur, nitrogen. You can't have more components than you have elements, so I'm going to go the whole hog and say I have six component system. Okay, so the number of components equals 6. The number of phases is clearly 3. Matte, slag, and gas. So the number of degrees of freedom is C minus P plus 2 equals 5. Okay, so with those components and those 3 phases, I have 5 things that I can fix. Okay, so what I fixed is the temperature, 1, total pressure, 2, PSO2, 3, PO2, 4, content of sulfur in the slag, 5, that's it, 0. Everything else now is going to be fixed. So yeah, the answer is yes. A-t-il raison? Oui, il a raison. Or if you had another system with exactly those 5 variables the same, you would have the same slag and matte composition of the 2 cases. And it doesn't matter what, I mean, the gas contains SO2, SO3, S3, S4, S5, S6, whatever, NO2, it doesn't matter. The gas is in equilibrium. The slag contain iron 3+, it contains sulfur, it doesn't matter how the sulfur's in there as an ion or whatever, or even sulfates. The whole thing's in equilibrium. That's what you got. But these 2 furnaces are not going to be identical. One could have like the ratio of the mass of the slag to the mass of the matte could be very different in the 2 furnaces, but their compositions will be the same. Okay, there's one more. Any questions? I lost this thing. All right, I gave you one other thing. This was the old exams. We go to number 30, old exams. And this was 2003 examen final, question 2. So there we have 2003. Maybe organize this a little better. Examen final, question 2. An isoplet of the carbon, iron, tungsten system is shown in the following figure. It's T versus weight percent carbon at constant weight percent tungsten. 5 fields indicated by question marks are not labeled. Put these labels on the diagram and draw the 0 phase fraction line of the body-centered cubic phase. And where is that diagram? Okay, so the weight percent tungsten is constant in this diagram. Iron's at the left, weight percent carbon, constant weight percent tungsten versus temperature. Okay, so there's your phase diagram. And I don't have an answer for this or not, another thing else. So, what are the phase fields there in the question mark? You can use two things you should be using then to think about this. Is well, first of all, you have the law of adjoining phase regions. When you pass across the phase boundary, one and only one phase changes. The other thing is the 4 phase nodes always look like this. Here you will have phases alpha 1, alpha 2, whatever. These phases alpha 1, the alpha 1, alpha 2 phases, there may be one of them, there may be any number of them, are common to alpha 1 plus alpha 2 plus are common to all 4 phase fields around the node. This phase field contains only the alpha phases. This phase field contains one more phase. This contains an additional one, gamma, and this one down here contains both the new ones. Okay, so using that and or the law of adjoining phase regions, you should be able to figure things out. So let's go up to this question mark here. You could look at different nodes. Let's look at this node. This node here. So this is the FCC phase, so that's your alpha 1. So FCC then should be common to this phase field, all 4 phase fields around this node. This, and this should all contain FCC. On this side they contain FCC plus WC. Down here they contain FCC plus liquid plus WC. So this is clearly FCC plus liquid. Okay, so alpha phase is FCC, the beta phase is WC, the gamma phase is liquid, and here you have alpha plus beta plus gamma. Or you could cross this line. Here you're going, let's say we go along this way. Here another phase appears, clearly, and here another phase disappears. So here the only real solution would be liquid, then you went liquid plus FCC, then you drop the liquid and went to FCC. Anyway, this region is liquid plus FCC. Any questions there? Or you could do it around this node here if you want. Send the same thing, FCC. Now your beta phase is BCC, your gamma phase is obviously liquid, so so this is FCC, FCC plus beta, FCC plus base C, so again you end up with FCC plus liquid over here. Let's look at this question mark here. Again, you can do it around this node, is probably your easiest. So again, you have FCC, the beta phase is WC, the gamma phase is M6C, so here you have FCC plus WC plus M6C. Okay, so you have all 3 phases, WC, M6C, and FCC. If you're trying to do these phases down here, things get a little bit more complicated. Probably your best bet for this phase, this region here, number 3. If we're trying to do region number 3, you kind of don't end up all the way over here. I would use, let's use the lava joining phase regions. This region over here is BCC, M6C, and WC. Here you have BCC, M6C, and FEW. So clearly when you cross, going from here, going left, when you cross this phase boundary, you drop the WC, and when you cross this phase boundary, you get the FEW. So this region 3 here then is BCC plus M6C. So the region 3 is BCC plus M6C. Okay. This region here, so let's do this one down here, this question mark over here first.
It can be BCC plus M6C plus WC plus FE2W. There is a possibility that we are getting WC. And
yeah, that's true. But then when you look over here, it's not going to work. So give me a second. Yeah, you're right. The lava joining phase regions doesn't give you the whole story. Yeah, if you just had those 2 regions, yes, you're right. It could be helpful. But here you can't be because you got this node here to consider. I'll give you that in a minute. Yeah. But let's look at this question mark over here. And we got to consider this node here, and you got to be careful because that is a horizontal line. So this line here is not a phase boundary. It's 2 phase. It's a very narrow 4-phase region. As you can see, this region up here is FCC, BCC, WC. That's this region. You go down to this region, 2 things have changed. Okay, you've lost the FCC and you've gained the carbon. Okay, so this really is not, this horizontal line over here is actually a very narrow 4-phase region that looks like that. These are your nodes. Okay, and here you have, over here you have FCC plus WC. That's this region. We already did this one here. That's the question mark, but that was FCC, what was it? FCC plus M6C plus WC. Okay, over here, this is the question mark region. Down here at the bottom, you've got BCC plus carbon plus WC. Okay, so this 4-phase region then is FCC plus BCC plus WC plus carbon is your 4-phase region. Okay, so you get your two-phase region, three-phase, four-phase. So clearly over here then you have FCC plus WC plus carbon around this point here. So this is not a node. You've got to spread out the four-phase region. This is your opened up four-phase region. In actual fact, the upper boundary and the lower boundary are coincident. Everybody happy with that? Okay, so let's go back now to this horizontal line. Again, that horizontal line is not a phase boundary. Just the fact that it's horizontal at constant temperature tells you immediately that it's not a phase boundary, it's a narrow three-phase region. Or again, you can see it if you go from this region and you cross this region here and you cross the boundary, two phases change. So I'm going to take this line here and I'm going to again open it up into an artificially opened region, and now we see the nodes go like this. So here we have FCC plus your N6C. Over here, the question mark region was FCC plus N6C plus WC. We worked that out previously. Over here you have FCC plus BCC plus M6C. So then clearly this has to, based on this node, this is FCC plus BCC plus M6C plus WC, which again then, when you had this question over here now, what this region number 3 was, this is your region number 3 over here. Okay, sorry, down here you have a node now. You have a region over here, which is BCC plus M6C plus WC. Okay, now I tried to find region number 3 before by using the law of adjoining phase regions, and as you pointed out, there's 2 possible solutions. But if you just look at that, but if you look at this here, then clearly this is the 2-phase region, 3-phase region, 4-phase region. So this region must be FCC plus M6. Sorry, BCC plus M6. And that then, over here now, you have FCC plus BCC plus WC, and so the final question mark here, this question mark phase here then, is clearly the BCC plus WC. Which you can also get from the law of adjoining phase regions going across this. Okay, so, and the final question then was trace the zero phase fraction line for the body-centered cubic phase. Remember, the zero phase fraction line is the line where the phase is on one side and not on the other. Okay, so let's start up here, and we go along this line. So the zero phase fraction line goes along here. Okay. After BCC is below, it's not above, so it goes over to here. Now we come back along the bottom line here. This is a 3-phase region, has BCC, and we've looked at this question mark and it doesn't contain BCC. So we're going down here, and we come back along here, along the lower line here to this node. Then we have to go along this curve here. Okay, because now the BCC is on this side, not on this side. So we're going to here, then along here, and now we're going along this curve down to this node. So far so good. Then we continue along this curve. Okay, because the BCC is over here but not here. So yeah. Okay, now we're going to be a little bit careful here because again we're going along somewhere, we're going to go along this line. But remember, when we've arrived here, so if you look at it open up, we've arrived here. We've not arrived at the bottom, we've arrived at the top. So we're going to go to the right or to the left. Okay, if we go to the right, we have BCC on one side and not the other. If we went to the left, we'd have BCC both sides. So we go along this way. So after arriving at this point, we move along here, along the top line to that point. Then we move, obviously, along here. And once again now, we're at the top. This is this four-phase region here. We're at the top of the four-phase region, not the bottom of the four-phase region. So in the same sense as here, we end up going out this side. Now there's an even simpler way, however, to look at these zero phase fraction line. Following the zero phase fraction line, which I didn't point out before, but if you have, every node has 4 points coming together, although you could have this degenerate thing. And what happens, say you're following the zero phase fraction line and you come into a node, there are 3 possible exits. Okay, the exit is always the center one. Just think about it. Come along here, we've arrived here. Now I have 3 possible exits. 1, 2, 3, I take the center one. Here, I've arrived at this point, the center one of the 3 possible exits are 1, 2, 3, I take the center one. This is the center one. I'm arriving here, remember 1, 2, I've come in this way. As I came down here, I came in this way. I could either go out this way, or this way. I take the center one, go out that way. You're always going out the center one. Come in, you take the one that's not the left, not the right, you take the middle road. Okay, there's some lesson for life to be learned there. Politics or whatever, I always say the centrist. Okay, will make you a good Canadian. All right, any questions about the...
So what's this phase BCC plus MCC plus F2W? This one.
This
Side one.
Huh?
Right side, this phase.
This region here
Yeah.
is that. So it should be done. Yeah, this region here is
I think the place
BCC.
of WC, it will be Fe2W.
I'm still not sure what you're...
So in the place of WC, that's BCC plus MC6 plus WC. So it will be BCC plus MC plus Fe2W.
Here?
No sir, right. Right.
Here. Here.
Yes.
This region
No,
is this
right.
region, which is this.
The line shown.
Okay. The line is right.
Yeah, the line goes there. It's a little confusing. This applies to this region. This applies to this region. Okay. All phase diagrams are that way. As long as you really have nodes where 4 lines come in, it's really trivial. It's when you get these degenerate lines that you have to be a bit careful about what you're doing. Okay, oh yeah, that was it. Any questions about the homework problems in general? Okay, so as I said, the quiz next, or test, whatever we call it now, next Wednesday is up to this point, including these problems, but nothing else. The material I'm going to talk about in the next hour is not on the quiz. But everything I talked about last week was. And okay, I've got them ready today, but Thursday I'll give you a number of homework problems that are just reviews if you want to look at them. For other things you might want to look at if you well, you can look at over any of the any of the series here, but I'll give you some specific ones that might be useful to look at. Okay, so let's take a break and come back. Ready, set, go.